And that's okay, folks. So my plan today is to start with the announcements. I figure a couple people may trickle in during that time frame. Then I'm gonna pass back your exams and your quiz 1. I still have got to grade the graphing lab. When you receive your exams back, if you look at the back of your exam, you're going to see how many points you missed. You will then see that I curved it by 3 points because there was one question I decided probably wasn't as fair as I'd like it to be because I hadn't gone over it. And then you'll see your percentage grade. Before I get, and then after I pass back everything, that's when I'll get into today's information. Though I may scroll up while I'm passing things back so that you can see the next piece and start making notes of all the equations and stuff. We'll get there. Now, it was brought to my attention that Active is doing something very funky with their grading. Don't look at Active's grades, look at what's in Blackboard. I checked it, what's in Blackboard is correct. Whatever's going on with Active, that I don't know, and I don't have control over that. That is done with their system, which is basically down in Texas. So I have no control over that, so check Blackboard for your grade. Now, I will say it normally does not upload until the next day. So I don't expect grades from today's quiz to upload until tomorrow type thing. But anyhow, pay attention to Blackboard, don't pay attention to Active. And if you ever see something that doesn't look right, definitely holler at me. And I will try to check it out and figure out what's going on. I'll have to talk to Active to see what's going on there. I just haven't had time today to check with Active after it was brought to my attention. So the other announcements, quiz number 4, it is due by 11:59 p.m. It's only 3 questions, one of which I tried to keep very simple, and then you got a couple to work on. I did give, I think, plenty of time to get those 3 questions in and done without you stressing too much. This week's lab is going to be the kinetics lab, which is the chapter that I hope to start at the end of class today, but at worst case scenario, we will be starting it Thursday. The kinetics ed puzzles are due on Wednesday at 11:59 p.m. in preparation for the lab on Thursday. Your aspirin lab is due when you walk in. So again, I only want 1 per group. Y'all need to be talking to each other. if you haven't already, make sure that you got somebody that's got the lab done. Or one per group. And if I hear of one person having to do it all, I will consider dropping the grades of the rest of the team. This is not a one-person effort. Labs are meant to reinforce topics taught in class. If I hear of just one person doing it, we'll be talking, because that is not cool in so many ways. And I just wanted to make note that on Sunday, you're gonna have 4 things due. They're all already uploaded. The homework number 5, these 3 Math Chem Ed puzzles are actually related to what we'll be doing in lab. They deal with method of initial rates, and they deal with first and second integrated rate laws. So they are very much related to what we'll be doing in the lab. The last thing, the majority of the grades were A's, B's, and C. I had a decent amount of C's, but most of them were A's and B's. Do you make below a C though? You need to come talk to me. We need to talk about what you did to study for this test. We need to figure out what method you need to use to study for the test. Because folks, that was the easiest test of the semester unless you're super mathematically inclined. So I want to help you figure out how to approach my class for the rest of the semester. Because you got to get that grade up. I do drop a test grade. So for those that did make below a C, this can be your test grade, but that means you got to score better on all the rest of the exams of this semester. So keep that in mind. And if anybody else wants to set up an appointment with me, if you got a C on it or a B or whatever, if you want to set up an appointment with me or come visit me, that's fine too. I'll see if I can't identify something that will help you as well. But for certain, anybody that scored below a C really does need to come talk, because we got to get that figured out. Any questions about the announcements for the week? Yes.
So the Math Chem Ed puzzles are different than the kinetics ed puzzles?
Yes.
Where will the Math Chem Ed?
There's a Math Chem Ed puzzle folder in the folder. It says Math Chem Ed puzzle, and then there is the kinetics, which are associated with the lab, is in the lab folder. So. Any other questions? Yes.
I noticed in Blackboard, we didn't do the sugar density, but I did the little puzzle videos. They're just gone now. Did you yank those out of there?
I did yank them out of there because they're not going to be associated with a grade. And so they would have been just sitting there staring at you and would have been, they're not going to get enveloped into a grade.
Okay.
I apologize for those that did it because I know that was a set of time, but at the same time, that's the reason I erased them. Other questions? Always ask me, folks. I have no problem answering. Before I pass this back, I'm going to actually get a little bit into it so that you can get to all the equations to start filling them out. So what we will be doing today is, the start of today is going to be talking about colligative properties associated with solutions. Basically, how does the introduction of a solute impact the solvent's properties? That's what colligative properties are. How does the introduction of a solute impact the solvent's properties? As we talk about this, we're going to talk about how soluble ionic solutes impact the solvent's properties. We're going to talk about how a non-volatile solute, a non-volatile covalent compound as the solute impacts the solvent's properties. And we're going to talk about how a volatile covalent compound impacts the solvents properties. Now, first things first. If you can't answer this question, that's the first question you got to be able to answer. How do you know if the compound's ionic or covalent? Anybody? What now? If you have an ionic compound, it will have a metal in it. You got to know that. Now, as far as whether it will be soluble ionic, well, that's another story. This comes back to your solubility rules, which you will be happy to know that I give you on the test. So, but it comes back to your solubility rules. Because if you have a soluble ionic compound, we have to take into account that that ionic compound dissociates into ions. And the number of ions are going to directly impact the solvent's properties. That bit about dissociating into ions is what is called the Van 't Hoff factor. Now, I will say this, if I look at sodium chloride has one sodium ion and one chloride ion. That would be 2 ions. Now, in reality, not all the sodium chloride dissociates perfectly. So we usually have a Van 't Hoff factor that is slightly lower than ideal. But here's the thing. If you are not given the Van 't Hoff factor, you're going to assume that it behaves ideally and dissociates entirely into its ions. So if I don't give you the Van 't Hoff factor for sodium chloride, you would assume that it is a 2. 1 sodium, 1 chloride. If I don't give you the Van 't Hoff factor for calcium chloride, you would assume it's 3 because that's 1 calcium ion and 2 chloride ions. So, soluble ionic compounds, we've got to take into account the Van 't Hoff factor. That Van 't Hoff factor is related to the number of ions that that compound dissociates into. So, now I will leave you writing equations and I will pass back a test in the quiz. And then in a few, I will move it up to the next section. So you got plenty of time. Junior, come on down. Kayla Applewhite. Can't remember if I have more than one Kayla in my class. And y'all can come up either way today. Caleb Ashley. Whoops, did I give him the, check the name? I think I swapped them. Y'all came up in the opposite order after all. Christian Bailey. Andrew Barker. Ian Blair. Madison Bowman. Calvin Burtis. Jeremiah Kennedy. Dylan Coates. Jasmine Khan. Rise. Danko? Danjo. That's the first thing. Still not the same. But I got the first name. Thomas Davis. Oops, thank you. Asia Deluge. Kelsey Dingler. My fingers will work. It would be nice.
Thank you so much.
Shelby Drumright. Nathaniel Fletcher. Oh, here's your quiz, Bryce. How it got messed up, I don't know. Nathaniel. Okay. Frank. Madison George. Ariston Glasgow. Okay, hopefully. One moment. Okay, hopefully this is better for all. Let me get back to where I was. Okay, so boiling point elevation, you're going to add the change in temperature. Freezing point depression, you're going to remove the change in temperature. To get to the change in temperature, that is going to be equal to the molality times the KB for the boiling point, where KB is a constant, so it has to be given to you. For the freezing point depression, it's KF, which again has to be given to you. So the K's are a constant here. So it's molality times K times I. And then for vapor pressure, the big deal there is when we're starting the vapor pressure, and I got distracted, obviously. The new vapor pressure is going to equal the mole fraction of the solvent times the original pressure for the solvent. But the mole fraction of the solvent is going to be the moles of the solvent divided by the moles of the solvent plus the moles of the solute, again times that Van 't Hoff factor. And we're going to do lots of problems momentarily. So now you'll notice that when we're dealing with the volatile and non-volatile covalent molecules, you're going to treat them identically, except for the vapor pressure. No matter whether you're dealing with a volatile compound or a non-volatile compound, they are treated the same for boiling point, melting or freezing point. The only difference is the vapor pressure. But you'll notice that these do not ever include that Van 't Hoff factor. That's the difference. So that's why you got to know that soluble ionic includes Van 't Hoff. Is it a non-volatile covalent? No Van 't Hoff. Or volatile covalent? No Van 't Hoff. Okay, so problems are the best thing to do. We're just going to keep it very simple to begin with. What is the boiling point of a 0.122 molal aqueous solution of potassium iodide? Well, potassium iodide dissociates to form potassium plus iodide. So in other words, it forms two ions. We're going to need that. In other words, we're going to use the Van 't Hoff factor of 2 in this case because it forms two ions. Now, to get the original temp, or to get the temperature, we're first gonna have to calculate our change in temperature of the boiling point. That's gonna be equal to the molality times KB times I. Now, the KB for this substance, for basically for water, because it said it's aqueous, so the solvent is water. The KB for water is equal to 0.512, and that is degrees Celsius per molality. So our change in temperature for our boiling point is going to equal the molality given of 0.122 molal times our KB of 0.512, that's degrees Celsius per molal, times our Van Hoff factor of 2. So the delta TB is equal to 0.125 degrees Celsius. But that isn't what we were asked to solve for. We're asked to solve for what's the boiling point. So our new temperature for our boiling point is going to equal the temperature it normally boils at, which is 100 degrees Celsius, plus 0.125 degrees Celsius, or in other words, 100.125 degrees Celsius. So the introduction of that Ki at this 0.122 molar did not impact the temperature greatly, but it still impacted the temperature.
Are they generally gonna be like that, where it's only a slight increase, or we get still at the bottom?
It all depends upon the concentration. The greater the concentration, the more particles that are going to be in the way. And so you would expect it to be a larger increase.
But is it gonna be like, say, like 100 degrees Celsius?
I would not know. You're never going to get that large of a change. It's usually. There is one that I saw that does a 40-degree change, and that's significant, but most of them are much smaller.
Are we gonna need to remember that delta KB or just KB for water, or will it always be?
You will not need to remember the K's, you will not need to remember the delta T equations. Now, you need to know basically what I did here. I expect you to be able to put that together,
Where you just add them? or-
where you add them together, because it's a boiling point elevation.
But we're given, I guess, the base boiling.
You won't get, unless it's water. If it's water, you're not giving it, because that's 0 for freezing point, 100 for boiling point. But if it's not water, I'll definitely give it to you. Okay, let's look at another one. One that's actually a useful piece of knowledge to know, instead of just a generic piece. Antifreeze consists of ethylene glycol. which has the formula C2H6O2, which is a non-volatile non-electrolyte. Calculate the boiling point. And freezing point. Of a 25.0% by mass solution of ethylene glycol in water. This is going to require you to use information you learned last week and this week. Very first thing I see, so let's talk about what I see. I see a 25% by mass. So that's going to be 25 grams of the ethylene glycol in 100 grams of solution. Now, what piece of information is that is the percentage going to get me to of the equation? Molality. So we're needing to convert this into the molality, which is going to be the moles of solute over kilograms of solvent. Okay, well, let's just start this. So we have 25 grams of C2H6O2. Get that into moles. With the fact that it's approximately 62 grams of C2H6O2 to 1 mole of C6H2O, C2H6O2. So that comes out to be 0.403 moles. So that took care of the numerator. Now we got to get the denominator. So we need kilograms of solvent, not solution. So we're going to use the fact that the solution is equal to the solvent plus the solute. So 100 grams is equal to my solvent plus the 25 grams. So the solvent comes out to be equal to 75 grams. Converting that into kilograms, that means it's 0.075 kilograms of solvent. So our molality is going to be equal to 0.403 moles of C2H2 or C2H6O2 divided by the 0.075 kilograms of solvent, which is water. And that comes out with a molality of 5.37 molal ethylene glycol. Now that we know the molality, we can use that to calculate our delta TB, which would equal our molality times KB times, well, molality times KB. Again, that's all you need in this particular one because we're not talking about a soluble ionic compound. So that's going to equal 5.37 molal. And because it said that it was in water, that means that it is going to have a boiling point constant of 0.512 degrees Celsius per molal. So our change in temperature is 2.75 degrees Celsius. So in other words, our new temperature is going to equal the 100 degrees Celsius plus for water plus 2.75 degrees Celsius due to the addition of the antifreeze to come out to 102.75 degrees Celsius.
Jen, where did you get the point, 512 degrees Celsius?
That is a constant.
Okay,
KB is a constant. KF is 2.
okay, so that would be good.
Yeah. Now, this question did ask for you to get to the temperature. The freezing point as well. So delta TF is equal to the molality times KF. Again, our molality is 5.37 molal. And when I look up the KF for water, it is 1.86 degrees Celsius per molal. Again, that's a constant for water. So we're now looking at a 9.988 degree change. Now for freezing point, it's freezing point depression, means it's got to go down. So our new temperature for the freezing point is going to be 0 degrees Celsius minus 9.988 degrees Celsius, or in other words, it's a negative 9.988 degrees Celsius is the new freezing point of our solution. Folks, we put antifreeze in a car for 2 reasons. It helps to keep everything from freezing up when it's super cold outside and burning up when it's super hot outside, because it altered the temperature of the freezing point and boiling point by putting in that antifreeze. Questions? I know it's a couple of minutes early, but not much. Where's my timer? It didn't go off. So it's time for us to take, there it goes. A 2-minute break, and then we're going to come back for some vapor pressure. But one would think that so the
It should, what would it be? Because if you think about it. You're looking at, this last one. Make it like the next speed. With maybe.
You're supposed to go for
Start out. It's only good, it will be. It was a year.
Oh, that's it.
The only thing that's weird is. Yeah, so I think as long as they're that target is right, since you're basing everything off of loss. Concentration. Right, the amount. But you're absorbing. Oh, sorry. You're absorbing. Even though the information. Is the same. Yeah, so that would be. I don't know anything about this. Yeah, I know. You can. There's some. It's just so. Speak for let's get back now. And do some paper pressure. Okay. So one thing I want to jump back a moment at our equation and for covalent molecules. We talked about non-volatile compared to volatile. How are we going to know which one you got? There's a good chance that you may not know what the compound is, right? I mean, you've never worked with it, and most of these compounds are organic, like Camphor. How are you going to know what you're working with? So there's a trick to knowing whether you got a volatile or a non-volatile. Number one, they may have to tell you, or they're going to have to give you two pressures. So if you have a volatile solute, they're going to have to tell you it's a volatile solute, or you're going to know it's a volatile solute because you're going to have a pressure both sides. That's your job to memory that this is probably volatile. If you get it two pressures, it's probably volatile. So that's how you should approach it. Get two pressures, say it's volatile. So that being said, at 20.0 degrees Celsius. The vapor pressure of acetone, which is CH3, COCH3, is 181.7 millimeters of mercury. And the vapor pressure of water is 17.5 millimeters of mercury. A solution is made by mixing 128.4 grams of water and 97.60 grams of acetone. What is the vapor pressure of the solution? Okay. Folks, what I noticed right off the bat is I did have two vapor pressures. So this is going to tell you that you will be needing the pressure, the new pressure is going to equal the mole fraction of one thing, which in this case will be water, times its pressure, plus the mole fraction of the acetone times its pressure. So in order to figure this out, we gotta have the mole fractions of our substances. So our first task is gonna be to get all this into mole. So you're gonna have 128.4 grams of water, and we're gonna get that into moles of water using its molar mass. Which comes out to be 7.13. We're gonna do the same thing for our acetone. Which is 58 grams per mole. And that's 1.68. Mole of our acetone. And if we look at the total number of moles, or moles of solution, that's going to be that number plus 7.13, which is 8.81. So now we can do the math. Because the new pressure is going to equal the mole fraction of water. So that's going to be 7.13 moles of water. Divided by the moles of solution, which is 8.81 moles of solution. Times water's pressure, which was 17.5 millimeters of mercury. Plus, it's going to be that for the acetone. So 1.68 moles of acetone. over 8.81 moles of solution times the vapor pressure of acetone 181.7 millimeters of mercury. And I got 48.8 millimeters of mercury as the new pressure. Now, you should always ask yourself, does it make sense? First thing you need to know about vapor pressure of a solution that contains a volatile solute is that the vapor pressure will wind up between the pressure of the solute and the pressure of the solvent. So again, anytime you have a volatile solute, the pressure of the solution will wind up between the pressure of the solute and the pressure of the solvent. The second thing you can do to check to see if you're on the right track is look at which one was in the most quantity. Water was in the most quantity at the lower vapor pressure. So the fact that this is at 50 makes sense because water was in a greater quantity compared to acetone, which was in the smaller quantity. And so we would expect it to be closer to water because there was more of it. Questions? Okay, let's look at another problem. What is the vapor pressure? Of an aqueous solution that has a solute mole fraction of 0.1000. The vapor pressure of water is 25.756 millimeters of mercury at 25 degrees Celsius. First of all, I noticed I only have one pressure. That's telling me that my solute is a non-volatile solute. So my new pressure is going to equal the mole fraction of the water, which is the solvent, times the pressure of the solvent. Making that distinction, remembering that it's about the solvent is important. Because if the mole fraction of the solute is 0.1000, and the mole fraction of a solution is equal to 1. That means that the mole fraction of the solvent, which is the water, had to be equal to 0.9000. Once you, again, you have to keep solvent and solution. You gotta keep those terms separate. And you gotta think of them as separate terms. So it was very important for me to realize that the equation deals with the solvent. And so I had to get to the solvent. But once you get there, it's easy because our new pressure is going to equal the 0.9000 mole fraction of water times the pressure of water, which was 25.756 millimeters of mercury. Or in other words, it is equal to 23.18. 0 millimeters of mercury. Questions? Let's look at another one. Yes, it's lots of examples. I'm trying to give you examples so that when you go to work in problems, you got examples, folks. And I'm gonna vary it up slightly again. How many grams of non-volatile compound B whose molar mass is equal to 97.80 grams per mole would be needed or would need to be added to 250 grams of water to produce a solution with a vapor pressure of 23.756 torr the vapor pressure of water at this temperature is 42.362 torr. Now, this one's kind of interesting because we actually have to work backwards. We were given the new pressure, which is 23.756 torr. We were given the old pressure or the original pressure of 42.362 torr. So that's going to allow us to backtrack into the mole fraction of our water, which is our which is the solvent. So 23.756 torr is equal to our mole fraction of the water times 42.362 torr. So the mole fraction of water is equal to 0.561. Now, before we get into using that mole fraction of water, we were also told that we had 250 grams of water. Which we can use the molar mass and get into moles of water. And that is 13.89. And we need that because we know that mole fraction for water is going to be equal to the moles of water over moles of solution, where that is equal to moles of water in the numerator, and the solution is equal to moles of water plus moles solute. So 0.561 is equal to 13.89 divided by 13.89 plus X. Multiplying through by the denominator. We get 7.79 plus 0.561 times X is equal to 13.89. I use the distributive property to simplify. So 0.561 times X is equal to 6.1. So the X is equal to 10.87. And that is moles of B. What now?
Where did the 7.7 come from?
By multiplying 13.89 times 0.561, because I had to use the distributive property. So I multiplied it both by both 13.89 and then the X.
Okay.
Now you can get to the answer, folks, because 10.87 moles, we were told the molar mass of this thing was way back up here, 97.8 grams to 1 mole. So that is, we need to add 1,063.4 grams of B, whatever B is, to the solution to change the vapor pressure that much. Question. What I'm trying to illustrate with all of the examples that I just gave you today. First of all, you can go forward. You can calculate, let's say the change in temperature, delta TB or delta TF. You can calculate the molality and then plug it into the equation to get those changes in temperature. But you can also know how the temperature changed and go in reverse and you come up with a molality. With this vapor pressure, I gave you a couple of examples where I determined the mole fraction. And from the mole fraction, multiplied it times the pressure to get the new vapor pressure. But then I wanted to show you this one because you can also go backwards to find out how much of the sample was added to cause that kind of change. So I want you to understand it. It's important to realize you can, yes, you can go forward, but you can also work in reverse so it gives you information as well. Questions?
Are you saying examples are gonna be on the timer for the school?
Not necessarily, I can't remember what from Friday, what I put on the homework. All I can say is I was trying to give you a variety of examples so that hopefully you have something to refer back to. I will, don't forget, I do have study session from 2:30 to 4:30 across the hall tomorrow, and I can help with homework too. Last week. Not today. Good morning. Okay. I will see you.
We seriously made it like, you're available.
I know I'm a vehicle, I'm a vehicle. You can conference at the end of that time for, you can I am free from 11 to 2 and then 12:30 to 2. Otherwise.
I just had a question about my exam. So on 14, we're given an extra about. Substance. And for this one, which is one ATM. I realized what I did. On it. For there, lined up, I just had it. I just erased it. So I was just wondering if I could get like.
Basically, if you can bring 15 up, I gave it to you as it was. I just didn't give anything below 350.
Okay.
No, it does not that way.
Okay.
We had the same question. I had originally gotten 330 on there, and I tried to put some ability to move to it. I still felt like I could pull one if we didn't. Yeah, I put 335. It's slightly right, but I still, I think it'd be. It had to be really, I think, perfect.
I know, it's not,
But so what was the range?
I gave everybody 350 to 4
Okay,
because it was a little bit above if this is lined up perfectly.
it's actually.
No. That's them trying, get me to water main.
I'm trying to make sure I'm on the right, and keep it close.
Probably not. It's in Portsmouth, and I don't think I want to go down there. I mean, that's where I'm from, but like, I don't.
It's just slightly close, it made it slightly.
Say pay for your lunch.
It's not, I mean, literally, okay, so I mean.
My dad might not.
And I knew I was being very particular, is because it's right.
I had a ruler and there, yeah. I don't know.
It's literally the difference between that part right there. Is where the ruler is off slightly. And I had to judge it by lining it up perfectly.
So she basically gave the answer. Yeah.
I did give him right, just.
Right.
I'm
Okay.
sorry.
No, I just want to make sure. I want to make sure. I just-
We can use it correct. Your thought is correct.
Right. That's what I'm getting.
It's just angling.
I'm gonna go.
Or
All right.
I guess.
You have my-
Maybe on a future
Maybe
test, maybe like.
On the fine.
Right, it might be on a file. Would there be like a full way to be sure? 'Cause I guess,
Like a plus or minus 10. That's what I was thinking, you would do plus or minus 350, but.
I gave 350 to 400. So that's why. It wasn't,
Oh, no, I'm not waiting.
I actually had it closer to 400 if it was exact lined up, but. I need to remember to get one that has. Has lines.
Okay.
Maybe if I don't remember it, I will draw lines somehow.
that'd be
I
great.
need to draw lines.
Right.
So,
Okay. Awesome. I don't want to not, make the same mistake.
I understand.
When's that, study session tomorrow?
2:30 to 4:30 across the hall on 105.
Thank you.
See you later. It's all together. So one set.
I'll see you tomorrow.
I will be here. I'm fixing to run now.
Any of the extra credit stuff coming up?
The only thing I know of is right off bat, it looks like they may not be doing they've always done science nights, but I got an email saying they may not be doing them this semester. So I'll have to come up with other options for y'all. Because apparently what I had planned is not gonna be happening.
And then how do you want our donation to the food pantry? Do you want me, do we have show